Okay, so we're going to continue our discussions on electron configuration. And within our discussions yesterday, we said that all atoms have an electron energy level. They have levels around them. And that those levels actually correspond to the principal quantum number. We wrote that down yesterday. And we also said that that principal quantum number will be the same as the period number on the periodic table. So here we have energy level 1, here we have energy level 2, energy level 3, energy level 4. Now, this is, like I told you yesterday, all models eventually break down. And the problem with this model is that they're not really circles. Okay? So these energy levels are not really circles. However, what is correct about this? Okay, well, there are distinct levels. How many energy levels do we know that there are? Up to 7. Okay, and everything after 4 is actually a repeat of 4. So they change from 1 to 2 to 3 to 4, and then 5, 6, and 7 are actually repeats of 4.
So what's the point of having
Because you need more spots to put electrons.
So we're going to ask about the worksheet after we finish this, right?
Yeah, we'll have some time to work on that at the end. Because part of our discussions may be clarifying about that. There are actually distinct levels. Okay, so there are actually distinct levels. All right? So yes, there's level 1. Yes, there's level 2. Now, within the levels, then there are sublevels. And those sublevels are what we talked about as being the S sublevel, the P sublevel, the D sublevel, and the F sublevel. Now remember that not all of those sublevels exist in all the energy levels. Energy level 1 only contains an S. Okay? Energy level 2 contains an S and a P. Energy level 3 contains an S, a P, and a D. And everything from 4 on contains an S, a P, a D, and an F sublevel. And then within each of those sublevels, there are then orbits where the electrons are actually found. All right? And we said yesterday that our S orbit could contain, or that our S could contain one orbit, which would be 2 electrons. Our P actually has 3 lobes, which represents 3 orbits, which would be 6 electrons. The D has 5 orbits, or 5 lobes, or 5, orbital areas, each holding 2, so up to 10 electrons. And then our F has 7, holding an additional 14. All right? And so that's the basics of where we were yesterday. Let's see. That's why. All right. Hey, there we go. If we do that, then it'll roll. All right. So that is that. Let's actually go ahead and clear that. So our electron orbital then is the region where we have a probability, specifically a 90% probability of finding an electron. All right. And that is what we just talked about, that you have 1 orbital within the S, 3 within the P, 5 within the D, and 7 within the F. And let's just look at that real quickly. And these are all our slides from yesterday. So remember that the S's have a generally spherical shape. That does not mean that the electrons orbit in a circle. That means that there's a 90% chance of their being found within that spherically enclosed area. Okay? Yes? All right. So that is the S. In the p orbital, there are 3 lobes or 3 orbitals. The p sublevel, 3 orbitals or 3 lobes. One in the x, one in the y, and one in the z. And again, 2 electrons each, and that just represents the probability that it will be found in that area. D begins to take on an even stranger shape. We start to get kind of some double dumbbell or egg shapes, and then one of them actually is like a little couple of eggs with a donut. So you've got a short order breakfast right there. And then the F orbitals, of course, are just completely bizarre, and I'm not going to try and describe their shape. Yeah, I said I wouldn't, so I won't. All right. Question, and of course you can see that there are 1, 2, 3, 4, 5, 6, 7 F orbitals within that F sublevel, and so that will then hold 14. Hey, any questions so far about that? We hit on all that yesterday. Questions about any of that? No? All right. Let's see. We filled that in yesterday. Here's where I want us to come to now. And we looked at this yesterday. We looked at the idea of your periodic table, and if we're adding electrons, we add them first to the 1s level, then to the 2s level, then to the 2p level, then to the 3s and the 3p. And so you can see that as you move further down the periodic table, you're going to have more and more electrons with your element. And let's see, like this is lithium. Ooh, yeah, we don't need. All right, let's go back to the small and the pink. So here we have lithium. Okay, lithium. Find it on the periodic chart. There it is. What's its atomic number?
3.
Which means 3 protons. And then how many electrons?
3.
Yeah, in a neutral atom, the number of electrons will match the number of protons. All right, so it's got 3 electrons. Where are we going to stash those? Well, we'll start filling up the 1s orbital. Okay, and so lithium's electron configuration, we're going to start by filling in the 1s. Okay, and so we'll put 1 electron there. And then we'll put a second one in this 1s. And so we're going to say, hey, we've put 2 electrons in the 1s orbital. So at that point, that's full. Next, we're going to go to 2s. Now, that can hold up to 2, but I really only need it to hold 1. So I'm just going to stop there, and I'm going to say, hey, lithium, 1s2, 2s1, and that is what we call its electron configuration.
That's how you name it?
That's how you would denote its electron configuration. And so
That's on the worksheet.
if I were just going to name it, I would just call it lithium. Or if I wanted to, I don't remember if there's isotopes of lithium, but, lithium-3. If I wanted to. Now, when I would draw this would be if I were asked for its electron configuration. Okay, and so if I were asked for its electron configuration, this would be what I would put, because this tells me where the electrons are in terms of which orbitals they're in. All right? Hey, how do we feel about that?
Can you do,
Yeah, let's do another one.
can you do cobalt?
All right, tell me where cobalt is. Let's see.
It's gonna be 1.
Okay, you picked 27. Hey, before we do 27, how you feel about phosphorus?
Phosphorus, it'll be,
No, and you like that one? Sure. All right, phosphorus. Hey, so that's third one over, second one down. So let's see, looks like right here.
yes, sir.
Yeah, it's in the 5A group. And so phosphorus, its atomic number, if we were just going to write that, its atomic number is 15. So let's write its electron configuration. Now, I'm just going to start here, and I'm just going to start going across. Okay? What's it, atomic number 15, which means how many electrons do I need to get stashed?
15.
15. So the first 2 are going to go into 1s. So I'm going to fill up the 1s orbital. What's the next orbital that I fill up?
2s.
2s. And that's going to hold 2 as well. Then I'm going to come across here to the 2p orbital.
It's gonna hold 6.
And I've got my x, my y, my z. That's going to hold 6. Well, I'm still not to 15, so I'm still filling these up. 2p6.
And 3s2.
All right, then I'm going to come here. All right, Jacob, you're doing outstanding, so I'm going to pause you for a minute and check and see if anyone else knows as well. So 3s2. All right. Now, someone not Jacob, what's the next shell that we're going to be filling? 3p. And how many do we have?
3.
1, 2, 3. Okay, so 3p3. And at that point, we've got, if you add those numbers up, you have 15 electrons. And so that is going to be my electron configuration. All right? Questions about that?
Yeah, I don't know what we did. I don't know what.
Okay. All right. So a couple of you just said, I don't know what we're doing. All right. So let me just quickly summarize where we are. Now, you realize that all of our atoms have a nucleus and then have electrons around the outside. Yes? Okay, I want to see a thumbs up that you understand that. Okay, good. So now, you understand that we have different numbers of protons and neutrons and different numbers of electrons, yes? Okay, so we're still doing thumbs ups. Okay. Now, those protons and neutrons are found in the nucleus. The electrons are found outside the nucleus, and specifically in particular areas called energy levels. Now, within those energy levels, okay, you will have sublevels, okay, and then within each sublevel you will have orbitals. And those orbitals are where the electrons actually stay. One of the other teachers used an analogy that I really liked about streets. She said the energy levels are like the streets. If you're like on 1st Street, 2nd Street, 3rd Street, 4th Street, okay? And then the sublevels are like houses. You've got the S house, maybe the P house. On 2nd Street, you have an S house and a P house. 3rd Street, you have an S house, a P house, and a D house. Okay, 4th Street, S, P, D, and F. All right, so you've got your street, which corresponds to the energy level. You've got your house, which corresponds to the sublevel. And then within the house, you've actually got rooms. Okay, and how many rooms? Well, an S house only has one room. Okay, one orbital. And it's got a bunk bed where you can actually put 2 electrons. All right, so that's our where do the electrons go. So right now we're actually looking at sort of writing down almost like the address and giving a description of where the different electrons are found. All right, does that help you a little bit? Thumbs up, thumbs down, thumbs sideways. Okay, hey, we're going to keep going, and we're going to see if another couple of examples will be helpful for you. All right. Let's see. I'm going to switch colors. I'm going to switch to black, and I'm going to pick cobalt this time because cobalt seems like a good one. Yes, ma'am. Yes, ma'am. Go ahead. All right. So cobalt is 1, 2, 3, 4, 5, 6, 7 over. 1, 2, 3, 4, 5, 6, 7 over. So there's cobalt. All right, right there. All right, and it happens to be number 27. Is that correct?
Yes, sir.
All right. So let's start listing this out. Again, and I'm actually going to erase just going to erase some of that. Let's see. I'm going to keep I'm going to keep this, but I'm going to erase the pink arrows so that I can get my my other arrows in there. All right. So, hey, 1s, 1s2. What's next? Somebody not Jacob? All right, we filled up 1s. It's done. So what's next? Go to the next row. 2s. Okay. So 2s2. And then 2p6. 3s2. Let's see, and then I'm gonna let me get this. Let me get that out of the way. All right. Hey, next is going to be 3p6. Hey, I want you to notice how we're just tracking along the periodic table here until we get to cobalt. All right. 3p6. All right, now here's the deal. You're like, but wait, there's a 3d orbital. Here's the thing. It turns out that it's actually easier to fill the 4s orbital before you fill the 3d. Why? Because in the third level, you've already got all these electrons that are repelling each other. All right? Remember that like charges repel each other? And so in the third level, you've already got all this electrical repulsion going on. And so it's actually easier to start filling the fourth level before we go back and fill in the third a little more. So 4s2. Now we start filling the 3d, and we go 1, 2, 3, 4, 5, 6, 7. 3d7, and that is the electron configuration for cobalt.
Can we do
Can we do what? Calcium?
calcium?
Well, calcium would just stop at 4s2, so it would actually be really similar to cobalt.
Okay, but like, would the third shell just like not be complete then?
Yeah, that's right. Okay, so let's talk about a couple of things. Hannah asked a great question. She said, what if we do calcium? Okay, so first of all, we're going to save cobalt, and I'm going to, we'll go on to calcium. Hey, so what if we look at calcium? It would be the same as what we had up here, all the way down to, now let's see, if I kind of backtrack, calcium is right there. So I wouldn't need the 3d7, so it would stop at 4s2. Okay? So I would have 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then that's where we would stop. All right, and Hannah has asked, so does that mean that the 3D just doesn't fill up? That's right. So the third shell is not completely full. Hey, but your third valence shell is. The valence shell is only made up of your s and your p orbitals. So we've got our 3s, at least for the most part. You can have some bonding take place in here, but but in general, we can talk about, when we talk about our valence, we're going to talk about for the s and the p. All right. Okay, hang on, Daniel. So Hannah, we would look here, and I would say that in the fourth shell, which is my outermost shell, I have 2 electrons. So I would say that that there are 2 valence electrons in calcium.
Okay.
All right.
So like, because our valence, the third valence shell is full, it's okay. It doesn't
Yeah.
need the D. Okay.
Now, it's going to fill in that fourth level a little bit before it goes back to the third level, because of the electron repulsion that's already happening in the third level. Daniel, what's up?
I don't even know how to do my question right now, because I think I got my answer.
Okay, you keep thinking. All right. All right, I'm going to go to Hannah and then a chance. Hannah,
What were we talking about with the valence electrons?
what were we talking about with what?
The valence electrons?
I just mentioned that that it was okay that we didn't fill in the 3D because technically our S and our P being full satisfies the octet rule, and it gets us all those 8 valence electrons, so we can go on to our 4th energy level.
Wait, how do you know that?
Because I just told you. Yeah. Hey, you're doing fine. Okay, keep going. I've sort of opened a door for you, but you're doing fine. We're going to look in there a little more later. All right. Here we go. All right.
Are you gonna answer my question?
I don't know. I'm not really feeling it.
All right.
No chance. Okay.
If you were gonna do like a potassium, would it just be 4s1?
Yeah. So instead of 4s2, it would be 4s1, and that would be, instead of calcium, that would be potassium.
But then wouldn't that make your valence shell on there?
Oh yeah, even with 2, our 4th valence shell is not full. And so that's why calcium is going to want to bond with something, because it's going to want to get that valence shell taken care of.
Okay, never mind. So no matter what, our 3rd valence shell, okay.
All right.
That just
Hey, so we're moving on here. Now, I want to, okay, Daniel, go ahead, and then I'm going to tell you guys something else.
What I was saying,
What about what?
what I was saying, probably be 4, no, it's going to be 3D what?
What, zinc?
Yes,
3D10.
3D10.
Uh-huh.
I thought it was just 8.
3D10.
How many can be there?
Up to 10.
Okay.
I'll come back to your question a little later.
Okay.
Oh yeah, because all of them.
All right.
Didn't it say the 4th
Hey.
shell,
Whoop.
32, right?
Up to 32.
And so that's,
Hey, before I take any more questions, so Braden, I see that hand. Okay, I see that hand. Oh man, I thought you had like a academic question. All right, no, go ahead. Hey, go ahead, man. You're fine.
well, it's 32, right?
Hey, shh, I'm going to take more questions in a minute. Right now, I'm going to teach you something else. Focus, please. I'm going to take more questions in a minute. Focus. All right. Hey, you can see that this can get pretty long. Okay. Cobalt is way up here. Calcium's way up here. What if I'm like, okay, everybody, get out your pen and paper and let's do actinium, which is number 89.
Wouldn't it be the same as the?
Okay. Or let's do uno, number 108.
But wouldn't it be the same as the 4th energy?
Except you see how I'm having to write all these numbers out?
Yeah.
You got to keep writing.
So like
Well, I know, but like we'll keep writing. It'll just be the same as.
All right. Hey, do you guys see? Look with me. Do you see that phosphorus was relatively short because we only had to get 15 electrons in there, right? Hey, cobalt though, we're having to get 27 in there, and so our list is getting a little longer. It took 2 lines. What if I pick something in here? What if I pick something down there? It's going to get super long. There's a shorthand, a shortcut that you can do. Okay? Let's say that I've got one. If you've got one that's going to start on the 4th energy level, what you can do is you can represent, like, well, let me do this one. Let's do argon. Okay? So let's do argon. All right? Now, argon. Hey, everybody look. Let's see. Anson, what's our first one to fill in for argon? 1s2. Excellent job. William, next. Bless you. 2s2. Lance. All right, 2p6. Somebody else? 3s2. Good. 3p6. Okay, whoop, and that's it. That's where it stops. Here's what I want you to see. You see how that is exactly the same as as this. You see how filling argon up to there is the same as this part of cobalt? So what I'm going to do is I'm going to rewrite cobalt but the way I'm going to rewrite it is by representing that first set of electrons like this. And so when I put argon, when I put that noble gas in brackets, it represents all the core electrons up to that point.
So, if we were,
And then I'm going to finish it out, 4s2, 3d7.
We're doing argon, right?
Well, I did. Okay, you gotta stay with me the whole time. Here's argon up here, and you see that I did argon. All right, all the way down to 3p6, and then you see that electron configuration is actually the beginning of cobalt.
So that's cobalt. Like that AR in the brackets
Is that AR in the brackets
is argon.
is shorthand for argon's electron configuration.
You can do that for everyone.
So here's what I'm going to do. Like let's say that I want to do this one. Okay? Second one on the fifth,
You'll do the KR
which happens to be
brackets.
zirconium. No, zirconium. ZR.
oh, you said the second one. Okay.
The second transition metal. So number 40,
Yeah,
or zirconium. So if I want to do zirconium,
You'll do the KR in brackets.
I'm going to do the KR in brackets.
And then finish it out with whatever else you need.
And then I'm going to finish it out. Krypton got me to there, and then I'm going to finish it out with
5s2.
5s2.
And then 4d2.
But it has to be a noble gas.
But it has to be a noble gas when you shorthand it. Okay? You cannot, like if I wanted to do zirconium, which is number 40, the one we just did, I can't say,
ZR brackets.
I can't do urbidium, Y. I can't do Y in brackets and then say, and, one more. You have to use a noble gas for your shorthand. Okay?
Wait, so like if I wanted to do gold, I would put xenon.
All right, so if you wanted to do gold, which is number 79, which is right here, I believe. Oops, nope, back to right there.
Yeah. So like I would do.
Yeah, it's one over from the.
Yeah. So
So
I would do xenon and then 6s2.
5d.
Well, here's the thing. You would do 6s2, and then you would do 4f14, and then you would do 5d9.
Oh.
Because those are put in.
Because you see that from there you actually have to loop down
Okay.
and catch that little
Yeah, that makes sense.
section before you come back to do the rest of the D's.
So to get like, what is that? Potassium? PO84?
Yep.
You do
Yeah.
two xenon, and then 6s2, 4f14, 5d10, and then 6 whatever.
All right. Hey, you guys are well on the way. I want to show you something else now. This is called orbital notation. So, I think you guys are doing really well on the electron configuration. I feel like you're doing well on, so let's just say, let's come back here just for a second.
Mr. Willis,
Yes, ma'am.
will we get a paper that looks like that? With the film thing?
With this,
Yes.
your periodic table, you can use your periodic table and just follow along. I'll show you how. Okay? But your periodic table has this same little asterisk so that you know to go down there.
Oh, I'm probably not on the right letter.
Well, you got to remember that this is your S block. Okay, let me be sure I've got my pink. Yeah. This is your S block. Okay, this is your S block. Let's see. This is your, ooh,
You have to put the plus now, the helium. That's not plus the helium.
that's your D block.
That's a fat.
That's a fat D block. That's a P block.
It's a fat one. No, you know what I was gonna say.
And then that's our F block. Okay.
Don't
Hey,
forget helium.
all right. And helium, of course, is the exception because the first electron, the first energy shell only has one S, which only contains two. So that technically is a part of the 1s2, but it really belongs with the noble gases because of its inertness. Hey, everybody focus, please. So you have to remember that you have your S block, your D block, your P block, and your F block. So you have to remember what those blocks are. But Kylie, if you can remember, hey, S has 2. You see how this is only 2 wide. P has 6. This is 6 wide. D has 10. This is 10 wide. F has 14. This is 14 wide. Okay? And so it really, with just a little bit of practice, you'll get that in your head. All right? All right.
For right now, I know you told us yesterday you don't really want us to, but can I take a picture of that for when I'm working on that?
All right. Everybody take a picture of this if you want to.
All right.
What did I miss with FS14?
Where does that
Holly's starting to do. Every time I
Yeah,
say
what's
this,
your
you're
phone?
All right. Well,
No, please, my phone's like buried in my backpack somewhere.
all right.
One person that.
We gotta move on.
Could you guys take a picture of it? Can you send it to me, please?
Uh-huh. All right. So everybody snap that. Your orbital filling table.
How I can get some.
All right.
Not like special pictures.
Hey, so let's press on, please, Ibrahim.
What about if you do the cell cell denied here? Well, Axiom says so denied there. I mean, now connects to the so when you do you don't want to.
Hey, I'm gonna come back and talk about that later. Okay, I'm gonna keep going for right now, but I will come back and address that. And it actually, the answer is right here on the board. Hey, I'm gonna ask you that if you're not asking me a question to be quiet. All right, you're keeping other people from hearing and generally kind of distracting stuff. All right, here we go. We're moving on. So let's see. That's our orbital filling table. So let's just look at and pick again phosphorus. Okay. So let's see. Phosphorus 1s2. Whoops. 2s2. 2p6, 3s2, and then 3p3. Here's what I want you guys to see. There's another notation. You remember I told you yesterday that each orbital can only hold 2 electrons, and that those electrons must have opposite spins. Okay, we talked about that yesterday. And we said that we could just call it an up spin and a down spin. All right? Yes?
Yes.
All right. And so I want to show you another visual picture for how this fills in. So I'm going to use this. So I'm going to use that line right there to represent the 1s orbital, and it's going to fill up and down. Now, then I've got my 2s orbital. All right. So we'll make another line. And it's going to fill up and down. Next, we're going to have 2p. Now, here's the thing. Remember that the p actually has 3 orbitals. Okay, so the 2p sublevel actually has 3 orbitals. And you would say to yourself, hey, I'll bet we can go up, down, up, down, up, down. And you would be wrong. Okay? It turns out that when you fill these in, first each, because you remember that each electron kind of wants its space. And so it's actually going to fill up, 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 or it could have filled down, down, down. It doesn't matter, but they all fill the same way. And they fill one in each. Then they come back and fill the other. All right?
It goes 1, 2, 3, 4, 5, 6.
Yes. All right. Let's see. Next is 3s. And again, it'll fill up, down. And then last is going to be 3p, which I wish I could write off here to the side, but I'm kind of out of space.
And you said it doesn't matter the order, right?
What do you mean?
So you could do like down up.
No, they need to match.
No, I mean like, if you make the first one down up, you can make all of them down. Is that what you're saying? What do you mean?
Like if the first
If you put one
down.
S down up, then you can put the rest of them down.
Oh,
Is that what you're saying?
well, we're probably gonna draw them up, down. That's just convention,
Okay.
but it doesn't matter. It could be down, up. I mean, sure, because we're not putting a certain electron, in a certain area. Hey, here's what I want you to see though: up, up, up.
Yeah.
All right, the spins match and they fill in singles before they come back and double up. Okay. Hey, this is like if you're loading on a bus to go to a volleyball tournament. Nobody puts 3 people in a seat or even 2 people in a seat until you have to. You start with 1 each. Okay, and then of course you make the freshmen double up first. All right, but nobody doubles up until all the seats are full. Same thing for electrons. Nobody doubles up until all the orbitals have at least 1. All right. Let's see. Hannah, what's up?
How does that change it? Like, so, you know how 2p goes up, 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 down, down, down,
Okay.
like how does that, like, differ from the 2x's going up and down?
Well, because P has 3 orbitals and will hold more electrons.
Oh.
All right. Hey, let's take a look at this. Here's a sample. Okay. Yes, ma'am. Go ahead. Hey, let's look at this sample. Lithium. First, our 1s, and so we've got up, down. Oh, nope, nobody wants to buy your product. There we go. Lithium, we've got an up and a down, and then we've got 1 more, and so it's just an up. Ooh, what about beryllium? Up, down, up, down. Boron, up, down, up, down, up. Carbon, up, down, up, down, up, up. Because we do not double up until after all of them are filled. Nitrogen, up, down, up, down, up, up, up.
How do you know whether it's up or down?
You don't. We're really just representing that they have to be opposite. Because they couldn't even measure this until into the 1990s. Which I know you're like, oh wow, that was forever ago. Sorta, but at the same time, it's not. It's pretty recent in terms of human history. All right, so let's see. Up, down, up, down, up, 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 down. All right, fluorine, up, down, up, down, up, 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 down, down. And then neon, up, down, up, down, up, 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 down, down, down. And here's our noble gas notation as we saw earlier. All of these are in energy level 2, which means that we're going to start with our noble gas from the first one, which is helium. Although, really, by writing helium, all you're saving is this. So I don't usually do that for helium. You can, though.
Or like oxygen and fluorine,
Okay.
does that mean their like spin is down?
Ah,
Last thing you said is
do you
down.
mean the What do you mean their spin is down?
Like their orbital notation.
So their orbital notation would be up, down, up, down, up, 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 and then one down here. Is that what you're asking?
Well, what does the orbital notation mean? Like why?
The orbital that's a good question. What does the orbital notation mean? The orbital notation,
Like I thought it was like linked with the electron spin.
it is. The orbital notation just shows you the electron. Electron. It shows you the electron filling, and honestly, the spin doesn't matter a whole lot. What matters is, check this out, Jacob. This is something that you didn't ask about, but I'm going to go ahead and include. The number of unpaired electrons actually has a lot to do with whether a metal is magnetic or not, or whether it can be ferromagnetic and whether it can be magnetized. So the fact that these are unpaired actually has a lot to do with the chemical properties of the atom. And so that's the reason that we present the orbital notation is in order to understand the order and whether the electrons as they fill are paired or not. Okay? Yes, ma'am?
How will I know which direction to write there?
Just always make them up and then come back and fill down. Or if you want to make them down and fill up, then that's fine. Just always fill all your orbitals with one before you come back and put in a second. Okay? Hey, last thing that I want to show you guys, and then I'm going to give you some time. You guys have done really well in terms of hanging in there. I see some of you are glazed over a little, and just hang in there, and you'll have a chance to review and ask some questions in just a moment. Lewis dot diagrams. Okay, so let me clear this. Let me click here, and all right. So a Lewis dot diagram is used to show the valence electrons, specifically the ones from the S and P orbitals. All right, and the way that we're going to show that is we're going to put the symbol in the middle. We're going to put the symbol in the middle, and then we're going to add dots to represent the electrons. All right, so we're going to add the dots to show the electrons. Here's what that will end up looking like. Oh man, hate that doesn't roll with it. That's okay. We'll just leave it. Hey, let's say that we want to do lithium. All right, so I'm going to put Li. Now, lithium, find it on the periodic chart. All right, it's atomic number 3. Its electron configuration 2s2 or 1s2, 2s1. But what I really need to know this time is that it's in group 1a. So lithium is in group 1a, which means it has how many valence electrons? 1. So I'm just going to put a dot right there. And that's all that there is to that.
So how do we do that on Google Docs for this?
Yeah. So Google Docs, you'd have to have a way to write on,
I did that on paper.
Yeah, if you did it on paper, that's fine.
Yeah, because you can go to like a I use.
All right. So, hey, let's talk about how we can record that on Google Docs in just a moment. Let's pick another one. I'm just going to pick nitrogen. Okay? Nitrogen. Now, it's in group 5A, which means we need 5. Ooh. So do I do like 1, 2, 3, 4, 5?
No, I feel like they're all
Down, probably.
Straight up line.
Wait, do you go like 2, 2, 1 to show like the S's? Reminds me.
Okay, so do you do 2, 2, 1 to show the S, the
That's
S?
not what I was talking about.
Okay. Here's what we're going to do. We're going to show the way that the electrons would try to distance from each other. Okay? Electrons socially distancing since forever. All right? And so they're going to, I know. And so you're going to first of all fill one on each side, then you're going to come back and fill in a second one. Okay?
So you do that with like 80, and you just keep going all the way around?
No. Remember, we're only doing valence electrons, and so there's only up to 8 valence electrons. Hey, real quick, let's do fluorine.
I had to do 80,000.
Real quickly, let's do fluorine. How many valence electrons for fluorine? 7. We see that it's in group 7A, and so it's got 7 valence electrons. All right, 1, 2, 3, 4, and then 5. And then if I were just going to have 6, I would actually put it across. But I've got 7, so I'm going to go ahead and go back and fill that in. Neon, want to represent all 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. What's in between nitrogen and fluorine? Oxygen?
I didn't do that intentionally.
1, 2, 3, 4, 5, 6. And so that is your introduction to Lewis dot diagrams, okay? We will make more use of them later when we talk about bonding, but that's all that you need to know about them right now today. All right? That is going to conclude our discussions